In the previous videos, we saw how the trigonometric functions were defined based on geometrical principles. Let's see how trigonometry is used in physics. The reason why you're going to see a lot of trigonometry in your introductory physics class is because you will be dealing with a lot of geometrical projections or orthogonal projections in specifically. Now, your instructor will not actually say those words because they're actually geometrical terms. What you will hear in your class is that there will be entities there and then you will be finding their components. So let me illustrate this with an example. Imagine you walked a certain displacement. That will most likely be the very first example here in your class, the displacement situations. So, and we know the distance d, but we also know that we have walked in some direction up and to the right, and we need an angle here measured from some line that we have previously defined as our reference line. So with that d and angle theta, the question is, in the process of me walking along that direction for that much distance, how far am I from that line, from my reference line? So for that, I will have to draw perpendicular back to that reference line. The side that is actually adjacent to the angle in this orange triangle is going to give me how far I have drifted along my reference line. I will mark it as d parallel, and we will call it the parallel component in the physics class. So for the other side, the opposite side, I will mark it as d perpendicular, and we will call it the perpendicular component. And now you can see how trigonometry here is going to be very useful. For the perpendicular component that is involved, that really relates to the side of the opposite side of the orange triangle, we will use the definition of sine. Sine theta was equal to the opposite side over the hypotenuse. For our orange triangle, that means d perpendicular over d. So now we know that the d perpendicular must be equal to d sine theta. Let's see what happens on the other hand with the parallel component. The parallel component is related to the length of the side that is adjacent to the angle theta in the orange triangle. So we will use the cosine function here, defined as the adjacent side over the hypotenuse. For the orange triangle, of course, that will mean the d parallel divided by d. So you see that will give us how much is the parallel component. D parallel will be d cosine theta. So far things are very straightforward. The issues arise here from the fact that in your introductory physics class, 90% of the cases you will have that reference line marked as X. And because of that, most likely you will not be working explicitly with parallel and perpendicular components, but you'll be calling them different names. For instance, once you have the reference line marked as X, you will most likely call the parallel component the X component. And so you can imagine, like 90 out of 100 problems, you will be setting up dx is equal to d cosine theta. And a time comes when you forget that X component is not always involved with cosine theta, but it happened because of the geometry. And then in the 91st problem, you have a displacement with the line x, but the angle is actually not measured from the x line, but from the y. And this is where some students just due to sheer habit make the mistake to say, well, the x component is going to be the cosine theta and the y is sine. Here is the example that this is not true, and you always have to go back to basic geometric and trigonometric rules. So let's look at this angle theta. How do we find how far we are from the x line and how much have we shifted along the x line? You still draw perpendicular from the end position back to the x, and that will be the y component. Then we have the side here. That will be the x component, which will tell us how much we have drifted or shifted along the x line. But we don't really have an angle. So what we do is we can take the y component and shift it to the left, so we can see that actually is going to appear as an adjacent side here to the angle theta, and we create a top right triangle. So we're going to work with a different right triangle here. This is going to be the x component, and it will be facing, now it will be the opposite side to the angle theta. So now, once we have established which component is the adjacent and which one is the opposite, then we can go to the trigonometric functions. We will use the cosine function now to determine the y component. Cosine of theta is always going to be equal to the parallel component along the y divided by d. So in this case, dy over d. So that will give me for the y component of d to be d cosine theta. The x component is the one facing the angle in the upper right triangle, so I'll have to use sine theta. Sine theta will be equal to dx over d, and so dx here will be d sine theta. Now, many clever students say, well, do we need to use this angle? Can we switch? And I'm sure you're clever that as well. And if you ask the question, can we actually switch to the other angle? The answer is yes. You're welcome to draw here, mark a second angle, phi, that is 90 minus theta, and work with that, because then you're back to the first situation where you have the angle given with respect to x. And in this situation, indeed, the x component will be related to the cosine, but this time not to the angle theta, but the cosine of the angle phi. So be careful and make sure you switch. The y component, of course, will be d sine theta. So in short, it doesn't matter which way you go. You just have to be aware and mindful about those angles and to which line they refer, so that you avoid those common mistakes.